So we now know what happens when we integrate a completely analytic function around a closed loop. That is, the closed loop encloses a region where f of z is completely analytic. So what happens now if f of z is not analytic everywhere inside the closed loop gamma? So suppose we have, I'm going to call the function a different name, phi, which has just one singularity, z0, somewhere inside the region defined by the closed loop gamma. So in the figure, gamma corresponds to the curve, this completed curve. So there's a gap here, but I'm saying if I complete this gap, I've got gamma is this curve which goes from A to E, round to F, and back to A again. So that's the integral we want to find. So to find it, what we do is we instead consider this path here, where we go from A to B, then round this circle to D, back to E, around here, and then back to A. Now, in this case, we just have a singularity here. This is actually a simple closed curve with no singularities inside it, because this singularity here is actually outside this curve A, B, C, D, E, F, A. Okay, so by Cauchy's theorem, that means that this integral of phi around this curve here, F, A, B, C, D, E, F, is 0. Next, what we do is we divide this integral into 4 bits. So we've got the integral from E to A, which is basically going all the way around here. Okay. Then we've got the integral from A to B, then the integral from B to D around this circle C, and then finally the integral from D to E. Then what we do is we consider the limit as A approaches E and B approaches D, as these lines get much closer and closer. Then what happens is that, well, this first integral, the integral from E to A, gets closer and closer to the integral that we actually want to find. We want to actually find the integral around here, enclosing a singularity. This integral cancels with this integral, because basically these are just two line integrals in opposite directions which are getting closer and closer. So they basically, the integral from here to here is going to be minus the integral from here to here. So this term and this cancel each other out. And then we're just left with this integral here, which effectively is just integrating around a circle around the singularity. So we can approximate this as a circle, which we'll call C. So what does that mean? We've got rid of this term and this term. We have 0 is equal to this integral around here plus the clockwise integral around here, which means that the integral we want to find around here is equal to minus the integral around C clockwise. But if we change the order, change the direction, then that's just minus the integral, the anti-clockwise integral. So what we've now shown is that the integral around here is actually just the same as the integral around a small circle. So we effectively can shrink this contour, gamma, simple closed curve is called a contour, by the way. We can shrink this contour to just a circle surrounding the singularity. So what we need to do now is just evaluate the integral of the contour integral of a circle around a singularity. So to do that, we can make the circle as small as we like, which means that we can use the Laurent series which describes functions with singularities near to the singularity. So the Laurent series, if you remember, let's look back quickly, hasn't gone here, contains a Taylor series part plus these bits with 1 over z minus z naught, which can represent the singularity. So basically we substitute, okay, what do we do? Well, we substitute the Laurent series into here, so into here, and then we say, well, dz, well, we're going to write z as z naught plus r times e to the I theta, just change variables. So if we do that, z equals z naught plus r times e to the I theta, and then differentiate, that gives us dz, this is a constant, r is a constant, so we just got r, di theta, that brings down an I, and we get e to the I theta times d theta. So that's what dz looks like. Okay. Now, when we integrate term by term, so we substitute the Laurent series into here, and then we just look, we just basically end up with a separate integral for each term in the Laurent series. That's what we mean by integrating term by term. Now the Taylor series terms, there's no problem with these. These are analytic. There's no, they don't go to infinity. So if we're integrating around a closed curve, integrating around a circle, these terms will all give you 0. So that just leaves the singular terms, the bn divided by z minus z naught to the n. So we look at each of those separately, and in the general case we've got bn over z minus z naught to the n. We then make our substitution, so z equals z naught plus r e to the I theta, and change variable. We're integrating theta, when we do this integral around the circle, from 0 to 2 pi, obviously. So in our new change of variables, this line integral just reduces to this, where we're integrating theta from 0 to 2 pi. And we just have to do this integral, which is not difficult to do. Notice we've substituted. So z minus z naught, remember, is r times e to the I theta, raising to the power n. That just gives us e to the I n theta and r to the n on the bottom. So what do we get? Well, the r's are just constants with respect to theta. They're not very interesting. Bn is a constant. The interesting thing is what happens with the e's, e to the I thetas. So we end up with e to the I theta minus e to the I 1 minus n times theta, which we need to integrate. So if we integrate e to the I times 1 minus n theta, that just brings us I times 1 minus n downstairs, which the i's cancel. This, of course, is only true if n is not 1. So as long as n is not 1, then we end up with this, and, well, we can express e to the I times 1 minus n theta as cos and sine, the Euler formula. These are all integers, n is an integer, so when we substitute 2 pi and 0, well, we just get the same value. This cancels out, so this expression cancels out and we get 0. This is if n is not 1. If n is 1, then what happens? Well, e to the I theta cancels the e to the I n theta. They're both the same thing. And we just, and n is 1, so the r's cancel. We just end up with I times bn integrated from 0 to 2 pi, which is simply 2 pi I b1, because n is 1. So when we do this integral, all we're left with is 2 pi I times b1. So we have this result here that the integral around the closed loop of something with a single singularity is equal to 2 pi I times b1, where b1 is the term in the Laurent series. Now, because it's so important, the quantity b1 in the Laurent series is given a special name. It's called the residue. So this is where the name calculus of residues comes from. And the residue theorem basically generalizes this to the case when you have more than one singularity inside the closed loop gamma. So the residue theorem states that if phi contains a finite number of isolated singularities located at z0, z1, and so on inside the closed loop, then the contour integral around that closed loop of phi is just 2 pi I times the sum of the residues at those singularities. So it's not difficult to see why that is. You can do exactly the same proof as for this result here. Basically, if these are your singularities at z0, z1, and z2, then you can choose this path, which is itself a simple closed loop. So the integral around this dotted line and this solid line here is going to be 0. The integral you want to find is with this completed, and that's going to turn out to be just the integral around here plus the integral around here the integral around here anticlockwise plus the integral around here anticlockwise plus the integral around here anticlockwise. Because all of these integrals here and these 6 integrals here will cancel each other out. Okay, so that's the residue theorem, which is the most important result probably in this course.